Hi, I'm Professor Goings, and welcome to the Math Professor's YouTube channel. If you're looking for videos explaining topics in mathematics ranging from algebra through calculus and more advanced topics, please consider checking out our playlists, and please subscribe to our channel. That said, let's go ahead and get into the current video. I want to take a look at what's called the Cauchy Condensation Test. Now, before I describe what the test is and how to apply it, let's take a look at a simple example. If I look at the harmonic series, harmonic series is the sum from 1 to infinity of 1 over n, which is simply 1 plus a half plus a third plus a fourth, or any other series for that matter. It turns out that we can determine convergence and divergence by using, we really don't need the entire series. I could actually, ignore the first term and only use the rest, or just ignore the first 3 terms and only use the rest. More formally, a series converges or diverges if and only if every single tail converges or diverges. And again, the main thing that I want to highlight is that the convergence or divergence of a series does not require the use or the analysis of every single term of the series. We can actually take a portion of them. Of course, we have to take at least an infinitely many of them because any finite series is finite. But the idea is that there's different ways that I can just extract a portion of a series and determine its convergence and divergence. Once again, let me now take a look at just for illustration purposes, let me look at the harmonic series and let me write out a few more terms. The main idea within the Cauchy condensation test is that, once again, I don't need every term in order to determine convergence and divergence. It turns out that if I take, say, the second term, so this would be the second term of the series, the fourth term of the series, the 8th term of the series, and so on down here, the 16th term, and so on, I can actually use those to determine convergence and divergence. Now, what's the relationship between these? Well, notice that this is the 2 to the first term, this is the 2 to the second term, 2 to the third term, and the 2 to the fourth term. So if I take the terms of the series that have an indice or an index of a power of 2, I extract those. I'm going to create a new sequence or a new series using that sequence of terms and determine convergence and divergence. So let me go ahead and state what the theorem says. Here's the statement of the theorem known as the Cauchy Condensation Test. If the terms of the sequence that construct the series are positive for every integer and they decrease to 0, then the series, the sum of an, converges or diverges if and only if the following series converges or diverges. I take the series from 1 to infinity. Now, as I illustrated just a moment ago, I'm going to extract the terms of the series whose index is a power of 2. That means, I'm going to leave a little space here because I have to include another term, but I'm going to take the terms of the sequence that are a power of 2. So notice when I take run through my indices here. Plug in 1, it'd be A2. Plug in 2, it'd be A4. Plug in 3, it'd be A8, etc. Now, it's not just, I have to just extract those terms. I also have to multiply by the value of the index. So it'd be 2A2, 4A4, 8A8, so on and so forth. That series converges or diverges if and only if the original series diverges. So let me see what we have here. An is positive for every n, decreases to 0. The original series converges or diverges if and only if this new series converges or diverges. Okay, so let me just make an aside comment here. This is a convergence test that is not typically taught in a standard Calculus 2 class at a university or a community college. But it is useful, it's applicable in a lot of situations, and quite frankly, it's not any more difficult to understand than the ratio test or the root test. So I think it's interesting to take a look at. Let's take a look at an example, and in particular, the series that I just mentioned prior to this, which was the harmonic series. So let's take a look at the harmonic series. Now, standard Calc 2 class is going to prove that this diverges using the integral test, right? Because the natural log goes off to infinity as the upper limit of integration goes to infinity. So this is a standard technique, integration, and you can show that that diverges. But let's just see how the Cauchy condensation test would apply to that. So let's say solution. Okay. What I'm going to do is I'm going to take the series from 1 to infinity. Now I look at the series that I have constructed within the theorem of the Cauchy condensation test, and it consists of two things. The power 2 to the n. Then I'm going to take the terms of the sequence that are part of the series, but only take the powers of 2, where the index is a power of 2. That means I'm going to, again, let me just write this as A2 to the n, and this would be equal to the sum 1 to infinity, 2 to the n. Now, for A2 to the n, now 2 to the n is my index variable as opposed to n. That means this would be 1 over 2 to the n, right? And if we look back at the a moment ago when I had the terms of the harmonic series written out, 1 plus a half plus a third plus a fourth, etc., the terms what we're interested in are the second, which is 1/2, the fourth, which was 1/4, so on and so forth. So if I plug in 1, I get 1 over 2. Plug in 2, I get 1 over 4. So these are the terms of the original series that I need, along with this coefficient of 2 to the n. Now, let's go ahead and simplify that. Of course, that reduces to the sum of 1. And what this turns into then is something where the divergence test would apply. Remember that in order for a series to converge, a sufficient but not, or a necessary but not sufficient condition is that the terms have to go to 0. And clearly, the sequence consisting of 1s just converges to 1, not 0, and therefore this diverges by the divergence test. Now this isn't going to happen every single time, but as we'll see in the next example, what happens with the Cauchy condensation test is I take a series and I convert it into a different series that I can apply another test to that I might be more familiar with. Okay. Clearly, integral test applies for this one, so we technically didn't need to use, this theorem. But let's take a look at the next example where we may or may not have a tool that we can determine convergence or divergence of it. So let's take a look at the sum from 1 over n of 1 over the natural log of n to the fourth. And let's actually start that at 2. Because if I plug in 1, of course, that'd be 1 over 0, which is undefined. All right, and let's go ahead and apply the Cauchy condensation test to this. All right, so solution. Quick note, remember earlier I said that a series is going to converge or diverge if and only if its tail is going to converge or diverge. Well, I guess it doesn't really matter in this case. Well, so this one starts at 1. I can really start my series anywhere. I could start the series at 10 if I wanted to, or 1,000. But again, at 1 it's going to be undefined anyway. All right, so let's go ahead and take the series that is in the theorem. So I take the 2 to the n is my coefficient, and then I've got 1 over the natural log of 2 to the n, and that whole thing to the 4th power. Okay. Now we're going to investigate that series. First thing I'm going to do is inside of the natural log, I have an exponent, which means we can bring that out front. That means the series that I'm working with is equivalent to this expression. And power of a product is the product of the powers. Therefore, I can write the series as follows. Okay. 1 over log 2 to the 4th is a constant. Constant factors can be brought outside the front of the series and do not play a role in the convergence or divergence. Now my task is to interpret this series. What we did is we took the original series and we converted it to something that we may have seen in a previous section. In particular, notice I've got power of n, and then I've got n to a power. We could use a couple different tests on that. I will look at using the root test, because since I've got a power of n, if I do a root of that, then I would just have a 2 on top, and then I have an nth root of n, which again is a common term that we know how to handle. So let's use the root test. Okay, and so the root test says that I'm going to compute the value consisting of the nth root of the absolute value of the terms of the corresponding sequence. Oh, limit at infinity of that. And this would be limit n goes to infinity. 2 to the n to the 4th for every integer are always positive. Therefore, I can drop the absolute value bars. That gives me the nth root of 2 to the n over n to the 4th. And nth root of the nth power is 2. And then on the bottom, that would be the nth root of n to the 4th, which I'm going to write as the nth root of n to the 4th. Now, the nth root of n as n goes to infinity is one of our common limits, and we know that that converges to 1. Therefore, this would be 2 over 1 to the 4th, which of course is 2. In particular, that is larger than 1. Okay, so now I came down to where I can make a conclusion. Using the root test, the value of rho is larger than 1. That means the series is divergent. Well, what series is divergent? That means that the series that we came up with right here okay, using the Cauchy Condensation Test is divergent, and that's equivalent to the original series also being divergent. Okay. Hope that was helpful. Hope that was interesting. Hopefully that helps you apply some convergence and divergence tests to a variety of series. In the next video, I will give a proof of the theorem if you're interested in watching that. Otherwise, thank you for watching, and please consider subscribing.